to inculcate interest in engineering education and to improve subject understanding. Electronics section of Shri Devi classes introduce new video on intrinsic semiconductors in the subject electronic devices and circuit. So let's start our video. In our last video, we have discussed that material got three class: conductor, insulator and semiconductors. The semiconductors are those material whose conductivity falls between those of conductor and insulator. If numerically we see their conductivity or resistivity got roughly 10 raised to power -3 and 10 raised to power +3 figure. If it is conductivity, then the unit would be Simon per meter, and if it is resistivity, the unit would be ohm into meter. But the interesting thing is that we can control conductivity of these semiconductor materials by several ways, and that results in so many useful applications. Now the most common semiconductor material which we people are nowadays using are silicon having atomic number 14, germanium having atomic number 32. Now these two are having 4 valence electrons, so they are tetravalent. Now other popular example is gallium arsenide, which is basically a 3-5 combination. Gallium got valency 3 and arsenic got valency 5. So it's a gallium arsenide is a 3-5 combination. If we see electronic configuration of silicon having atomic number 14, which is 1s2, 2s2, 2p6, both 1 and 2 orbits are fully filled, and in third orbit there are 4 electrons. And in germanium having 32 electrons, the first 3 orbits are completely filled and the fourth orbit got the same structure. The outer orbit, third in silicon and fourth in germanium, both got same structure, both have same crystalline structure, both have same covalent bonding, and so many properties of two are the same, and we will study both of those in our following videos. Whereas this gallium arsenide is different. It's a 3-5 combination, and if you see structure here, the gallium which got 3 valency got 3 arsenic neighbor, whereas arsenic having 5 valency got 5 gallium neighbor, whereas each silicon or germanium got 4 neighboring atoms. In the following section, we will discuss the same in detail. Silicon and germanium are the two most important semiconductor materials we people are using in our electronic devices. Both silicon and germanium are crystalline in structure and have tetrahedron structure, which form a pyramid and with one silicon at center and other 4 atoms at each vertices. Now both silicon and germanium have 4 valence electron in outer orbit, so both are tetravalent. And if you see, their structure is just like carbon in diamond form. Now each silicon atom has 4 orbital electron and have 4 neighbor silicon atom, and each silicon atom share 1 electron of its own with one of neighbor, and now a silicon atom has 4 of its own electron and 4 he got from neighbor atoms, and by that it form an octet and make bonding with nearby atoms. This planar diagram represent actual tetrahedral pyramid structure of silicon for simplicity. Since valence electrons are shared between 2 bonded atoms, so this bonding is called as covalent bonding. Gallium arsenide also has covalent bonding, but now electrons are shared between 2 different atoms. One is gallium and other one is arsenide. Now each atom, whether it is gallium or arsenic, is surrounded by atoms of complementary type. That means arsenic is surrounded by 5 gallium, whereas one gallium is surrounded by 3 arsenic. Now this arsenic provide 5 sharing electron to 5 gallium neighbors, whereas this gallium provide 3 sharing electrons to 3 neighbor arsenic, and this is how they form bonding between nearby atoms by sharing of valence electrons. This bonding is called covalent bonding, and the material behavior is called semiconductor behavior because its conductivity is between conductor and insulator. A semiconductor in pure form having crystalline structure is called intrinsic semiconductor. Now such intrinsic materials show their natural, inherent, internal self properties when impurity level is less than 1 in 10 raised to power 10 atoms. So it's a very high degree of purity which is required to form such materials. If you see a silicon or germanium type semiconductor material at 0 Kelvin condition, you find that these electrons got small energy with them and the atomic bonding is very strong, and electron cannot leave their parent atoms, and since there is no electron away from these bonded positions, so such material have absence of free charge carriers and material behaves like an insulator. In our last video, we have seen that semiconductor material are best illustrated by energy band diagrams, and in between lower valence band and upper conduction band there exists a forbidden gap, and this forbidden gap for silicon is 1.21 eV at 0 Kelvin, and for germanium it is bit smaller and is 0.78 eV, whereas for gallium arsenide it is 1.42 eV at 0 Kelvin. Now highest energy which electron can have at 0 Kelvin is called as Fermi energy, and this Fermi energy is just midway between this forbidden gap. So all electron have to remain in valence band only, so it is completely filled and there is no electron in conduction band, that is totally empty. So again, due to absence of electron in conduction band or due to absence of free electrons, the material behaves like a perfect insulator at 0 Kelvin. At room temperature condition, all electron of semiconductor material won't have the same energy. Few got energy more than what is required to hold an electron in an atomic bonding. That energy level is called as breaking energy. Now few electrons by temperature conditions or by thermal agitation got energy more than that bonding energy, and they break their respective covalent bond and assume a free state. Now these free electrons, as one is shown here, left a vacancy in covalent bond, and that vacancy is called as hole, and both electron and hole participate in electric conduction in these intrinsic semiconductor. The number of these electron and hole is roughly 1 in 10 raised to power 10 atoms in silicon semiconductor material, and the same is 100 in 10 raised to power 10 atoms in germanium, or 1 in 10 raised to power 8 atoms in germanium. That means at normal room conditions, germanium got around 100 to 1000 fold more free electrons than in silicon. The term free electron is applied to that electron which has separated from their fixed lattice position, as this one from this position, and this free electron will have a perfect random motion due to thermal agitations where it won't contribute in any charge transfer, but when you apply external voltage then it starts drifting in a particular direction and conduct charge and produce electric current. Now this breaking energy to form a free electron can be given by some other ways also apart from temperature, and it may be incidence of light energy or photons or a strike of an external particles or high energy radiations, say X-rays. An interesting part of semiconductor studies is the concept of hole. When a covalent bond breaks and produces a free electron, then that free electron leaves a vacancy in that covalent bonding, and we generally represent that by a small circuit, and we call this small circle as hole. Now corresponding to 4 valence electrons, we can assume that silicon got 4 proton charge and this silicon atom charge wise neutral. But if there is a vacancy of electron in a covalent bonding or there exists a hole surrounding to any atom, then that atom got 4 proton charge but only 3 orbital electrons, so it have a surplus positive charge. So we say that hole position is a charged position, and this charge position won't remain at its own position, and what actually it do, it call any nearby bonded electron to fill this gap, and when this electron will move to fill this position, the end results comes as that the previous vacant position get filled, and at new positions from where we have this electron movement will have a hole position. So we can say that the earlier surplus positive charge which associate with this atom now has shifted to another position. So by the shift of bonded electrons at hole vacant positions, we got shift of charge or movement of charge. So we say hole is a charge carrier. Now the interesting fact is that to be a free electrons need quite a high energy, and an energy that is required to fill a vacant position to nearby position is quite small compared to that bonding energy. So it is very likely that any vacant position could be filled by any nearby bonded electrons. We found that when a bonded electron shifts, the whole movement is opposite to the movement of electron flow, and this whole movement flow direction is also known as conventional direction of current flow. So we treat hole as a virtual positive charge because in actual practice there is no positive charge which has moved, but the end result of shift of bonded electron is that positive charge associated with nucleus had changed its position. So hole is a charge and is movable, so it's a carrier and virtual positive charge carrier. Our thermal agitations continuously generate electron hole pairs, and when a pair is generated, both free electron and hole are produced in equal number. If this phenomena goes on in continuation, the number should increase with time, but we find that number product of electron and hole for a given temperature condition will not increase with time but will remain constant. Why this take place? The reason is, in a semiconductor material, a free electron can also occupy hole position, and in that condition both electron and hole pair will disappear. Now this act of mixing of free electron with a valence vacant position is called as act of recombination. Now Albert Einstein found that rate of recombination is directly proportional to number product of electron and holes. If electron and hole number are steady and temperature is continuously breaking electron hole and producing electron hole pairs, and there exist a steady conditions, that means the rate of pair production by temperature agitation and rate of recombination from number product of both carriers are in equilibrium. Now if we increase temperature, it is certain that more number will be produced by thermal agitations of electron and hole. So for equilibrium state, there should be more amount of recombination, and the recombination is only increased by increase of number product of electron and hole. So we can say that if temperature is increased, the number product of electron and hole will also increase in all semiconductor materials. Now this law is called as mass action law. So we can say that number product of electron and hole depends on temperature. In a pure intrinsic semiconductor, both free electrons and holes are equal in number, and this number is called as intrinsic number. And as per our law of mass action, number product of electron and hole is a function of temperature only. So if the number are equal, then Ni square is given by this temperature governed relation, where A is a material constant which is higher for germanium and smaller for silicon. Now EZ is called forbidden energy gap, and we'll soon see what exactly it is, and it is 1.12 eV at room temperature condition for silicon and 0.72 eV for germanium. Now this K is Boltzmann constant having value in electron volt per Kelvin unit 8.62 into 10 to the power 3, and this T is degree Kelvin temperature. Now you can see, if you increase temperature, whether this TQ factor is there or this exponent negative power is concerned, this number will increase. So intrinsic charge carrier concentration increases in an exponent manner when we increase temperature, and since this A is higher for germanium and EZ is smaller for germanium, so germanium is more sensitive to temperature than silicon. So to safeguard our electronic circuit from temperature variation conditions, we prefer and use silicon more than germanium. Now when we increase temperature, this intrinsic number increases, so the conductivity of semiconductor also increases, and it is found that number will double for every increase of temperature, approximately 8 degrees Celsius in silicon and 6 degrees Celsius in germanium. Let's make an interesting comparison between three common semiconductor materials. In the beginning of our electronics during 50s and 60s of last century, germanium was most exclusively used semiconductor material because silicon was very difficult to refine at that time, and relatively germanium was easy to refine, easily it is available, and it can be easily fabricated. But due to the problem of temperature sensitivity, the reliability of germanium devices is not good. So silicon has replaced germanium, though it is difficult to refine and fabrication, but the technical advancement have made silicon the most common semiconductor material of choice because silicon was less temperature sensitive and also easily available in our earth. Now this is all done by the recent technical advancement of silicon processing. The common silica sand is not crystalline. Now what we do, we spun silicon at a very high speed and generate crystalline structure, and then we slice small wafers, and by those small wafers we produce electronic devices. Nowadays we have a new semiconductor material, GaAs, now which can work at higher speeds, even 5 times more than that of silicon circuits. Since we have lots of years of experience of using silicon in our electronic devices, so silicon technology is cheaper, and we have so many high energy efficient design strategies available in silicon circuits. So still the silicon is fundamental building block of all our new electronic components, ICs, or even complex processor. But the demand of increased speed resulted in more research and development in gallium arsenide devices, and today GaAs is often used in very large scale integrated circuit designs, and all our LEDs got GaAs as one of the base material. When we apply external voltage, there exists an internal electric field which is directed from high potential to low potential in semiconductor material. Now this electric field shifts thermal motion of free electrons as well as holes in a one particular direction, and electron will drift opposite to the direction of electric field, and hole will also drift in the direction of electric field. Now when a hole drifts, it means some bonded electrons are moving in an opposite direction. So in semiconductor we have both free electrons and bonded electron through hole positions participate in electric conduction, and the total conductivity of intrinsic semiconductor is sum total of two contributions, one from free electron and one from hole. So the total conductivity of intrinsic semiconductor is sum of conductivity due to electrons and conductivity from hole. Now we know conductivity got a relation Ne mu, where N is number density of charge carrier and mu is mobility. Now in a semiconductor material, hole number is equal to electron number, and that number is called Ni. The charge of electron as well as hole is the same, but the mobility of two is not the same. Electron is more mobile, and when you apply electric field, its drift velocities are much more than that of hole. The drift velocity or mobility of hole is half in case of silicon compared to electron mobility, and is 1/3 in germanium as compared to electron mobility. So hole is less mobile than electron. So in mathematical modeling of conductivity calculations, we treat hole as a virtual positive particle of mass say double or 3 times that of mass of electron. And look, when we increase temperature, we have seen that this intrinsic number will increase, and this increase will increase conductivity of semiconductor materials when temperature is increased. Most interesting way to understand semiconductor electronics is energy band diagrams. We have given detail of energy bands in our last video, and link is given in description. Let's study the same in detail. Now the energy band diagram is understood by a parameter called as Fermi Dirac probability function. Now the Fermi Dirac statistics says that all electrons of a material got different energy conditions, and this probability function of Fermi Dirac specify how much amount of particular energy state is in comparison to all states under thermal equilibrium, or this probability function specifies the fraction of all states of particular energy E level occupied by electrons under thermal equilibriums. This study is applicable when temperature is not changing. Now if we use quantum mechanics, then this Fermi Dirac probability function is given by this mathematical expression. Here this E is not electronic charge, but it's irrational number called as exponent, which is roughly 2.718. Now this K is Boltzmann constant. In EV per Kelvin unit, it is 8.62 into 10 to the power 3. Now E is that energy for which we have to find out probability of existence, and EF is a particular energy level which depends upon material composition and temperature conditions. Now a plot of this probability function with energy values is shown here, and it is clear that this distribution become a rectangle shape for 0 Kelvin conditions, and it got a typical shape at higher temperatures, and the curvature of same will reduce when you increase temperature. And it is very interesting that there is a particular energy where this probability function become halfway 0.5. Now this particular energy value is called as Fermi energy. Let's understand what exactly the Fermi energy is. This quantity EF is called Fermi energy level, which represent occupation probability of 50% for a particular energy value for any condition of temperature other than 0 Kelvin. It means half of electron have energy below this value and half of electrons have energy above this level. So this is demarcation of energy value for 50-50 number. Let's understand it. Now the Fermi-Dirac probability function is given by this expression, and if this E become EF, then this figure becomes 0 and exponent power 0 is 1 and the calculation comes as 0.5 or 50%. So this level is 50%. But the interesting thing is that means 50% electrons got energy less than this and 50% got more than this. But look, all electrons won't have same energy. Those electrons which are very close to this level got higher numbers and those which are at higher value got smaller numbers. Let's understand what is importance of this Fermi-Dirac energy distribution. Suppose I need number of electrons which are more than of this level. Then if I make integration of this probability function with energy or calculate this area, then this area between curve and energy axis represent the total number of electrons which are having energy more than this. So you can say that half of electron got energy more than EF and half got energy less than EF. Let's understand Fermi-Dirac probability function for 0 Kelvin conditions. This rectangle shape at T equal to 0 Kelvin, this KT becomes 0, and for E greater than EF, this become positive infinity and exponent with positive power become infinite and this becomes 0. That means number of electrons above Fermi energy is 0 at 0 Kelvin. And similarly for E less than EF, if you make calculation, then this become a negative infinite or 0. So this ratio become 1. So almost all 100% electrons got their energy less than this value for 0 Kelvin conditions. So when you increase temperature, the most energetic electron got its energy increased, and it is much more in case of very high temperature, and it is quite more at such room temperature 300 Kelvin. Let's conclude our study of intrinsic semiconductor. The calculation says that this 50-50 level or Fermi energy level lies just midway of this forbidden gap. Now at 0 Kelvin, this 50-50 level is not 50-50 level, but in fact all electrons have energy less than this level. So they all have to remain in this valence band, and this conduction band is totally empty. So there is no electron in conduction band at 0 Kelvin. So there will be no conductivity and material will behave like a perfect insulator. Now at room temperature condition of 300 Kelvin, this highest energy of valence band increase a little bit. So this 50-50 level or Fermi energy level also increase a little bit. So this forbidden energy gap has reduced a bit. Now if you see the previous picture, few electrons got energy more than this gap and they will reach to conduction band, and when an electron moved to conduction band, it left a vacancy in valence bond, and in this vacancy these bonded electron can make shift and can participate in electric conduction. So we say that at room temperature condition, few electrons in conduction band and equal number of holes in valence bond participate and produce little bit of conductivity in semiconductor materials. Now intrinsic semiconductor got very few application in our semiconductor electronics, such as measurement of strain, etc. In fact, useful material becomes when we add impurity in a designed manner in pure form of semiconductor, and such doped semiconductor is called extrinsic semiconductors. In our next video we'll learn about extrinsic semiconductors. Semiconductor material got huge number of application in our life. From district headquarter Hanumangarh in northern Rajasthan, we have started Shri Devi classes YouTube channel to ease out science and engineering learning. अगर आप हिंदी भाषी हैं तो अपनी मातृभाषा हिंदी में भी इस डिप्लोमा इलेक्ट्रॉनिक्स इंजीनियरिंग के बेस्ट ई लर्निंग मटेरियल को देख सकते हैं. द लिंक फॉर द सेम इज गिवन इन डिस्क्रिप्शन. आवर एक्सपर्ट एंड caring teachers has produced the best e-learning material for your diploma electronics engineering studies. We have used the standard text material and scientific method of explanation. That this will save your time and improve your subject understanding. It is also very good for fast revision and scoring high in your examination. It was well said, knowledge increases when you share. So please do subscribe and share Shridevi classes. You would learn better, achieve success and attain great height. Happy learning.